All right. Hey, everyone. Gearing up for that Math 218 final? Well, you've come to the perfect spot. This is going to be your Power Up, a super fast crash course on all the core stuff you absolutely have to know to crush that exam.
So here's the game plan. We're going to start with solving systems, then get into the story of rank, the decisive determinant, and the big invertibility test. We'll wrap it all up with how matrices are actually transformations. We're going to build this from the ground up, moving from a concrete problem to some really powerful big ideas. Okay, let's dive in. Okay, first up, solving the system. This is really the fundamental problem of linear algebra. So you've seen a system of linear equations like this before, right? You've got to find x, y, and z. Now, the very first thing we do in linear algebra is clean this mess up. We're going to strip out all the letters, the plus signs, the equal signs, and just focus on the numbers. We'll put them into a nice, neat grid called an augmented matrix. It's just a much cleaner way to see what's really going on.
And there it is. See? Same problem, just way more organized. All we did was pull out the numbers, the coefficients, and line them up. And this simple little grid, it's super powerful. It's what lets us use a really slick, systematic method to find the solution, a method called Gaussian Elimination.
So this is our playbook, Gaussian Elimination. The goal here is to use a few simple moves. We call them elementary row operations, stuff like swapping rows or multiplying a row by a number, to chip away at this matrix. We're trying to sculpt it into this nice staircase pattern with leading ones and zeros underneath. Once we get it into that shape, what's called row echelon form, solving the system becomes, well, it becomes almost trivial. But hang on a second. Does this process always give us one perfect, unique answer? Like x is 5, y equals 2. The answer is no. Sometimes there are infinite solutions, and sometimes there's no solution at all. So the big question is, how can we look at that final matrix and know what kind of solution we're dealing with? And that question leads us right into our next big topic, the story of rank. This is how we start understanding our solutions on a deeper level. Now, the word rank sounds kind of fancy, but don't let it throw you. All it is, it's just counting the number of non-zero rows, or those leading ones we made after you've done all your row operations. It's that simple. But this one little number, oh man, it tells you a huge story about your system of equations. Okay, case 1. This is the dream scenario, right? The rank, which we're calling R, is the same as the number of variables you have, n. If that happens, boom, you've got one single unique solution. No fuss, no muss, the answer is the answer. Now, what happens if the rank is less than the number of variables? This is case 2. You'll see this when you get a row of all zeros. What does that mean? It basically means one of your original equations was a copycat. It wasn't giving you any new information. So because we're missing a piece of the puzzle, we end up with what we call free variables. You can plug in almost anything for them, which means you have infinitely many solutions. And then there's case 3, the total contradiction. This is when you're doing your row operations and you end up with a line that says something like 0 equals 1. Wait, what? 0 can't equal 1. It's a mathematical impossibility. If you see this, you stop right there. The system is inconsistent. There's no solution, period. All right, so Gaussian elimination works, for sure. But it can be a lot of number crunching, right? Especially if you just want to know if there's a unique solution before you even start. Wouldn't it be great to have a shortcut? Well, there is. And it brings us to this kind of secret number hidden inside every matrix, the determinant. The determinant is this one special number you can squeeze out of any square matrix. Think of it like a quick blood test for your matrix. Before you do the full complicated surgery of Gaussian elimination, you can just calculate this one number and it'll tell you the health of the system, specifically if a unique solution is even possible. So how do we calculate this thing? For a little 2x2 matrix, it's super easy. You just multiply down the man diagonal, A times D, and then subtract the product of the other diagonal, B times C. That's it, 80 minus BC, done. Okay, for a 3x3, it gets a little bigger, but there's a cool visual trick. You basically draw these diagonal lines. You multiply the numbers on the 3 downright diagonals and add them all up. Then you multiply the numbers on the 3 upright diagonals and subtract that whole chunk. It's a bit of arithmetic, but it's a surefire way to get to that one magic number. So why are we doing all this? What is the point of this one number?
Well, this gets us to the determinant's true power. Because this number, it's the ultimate test. It tells you if your matrix has a very special property, whether it's invertible. Okay, this slide right here, this is the Rosetta Stone. It connects everything we've talked about. And the rule is so simple. If the determinant is anything other than 0, the door is unlocked. Your matrix is invertible. It has full rank. Your system will have one beautiful, unique solution. But if the determinant is exactly 0, the key breaks in the lock. The matrix is not invertible, its rank is less than it should be, and you're stuck with either infinite solutions or no solution. You have got to remember this for the exam. Now, you are almost guaranteed to see a question on your exam that looks something like this. They'll ask you to find the value of lambda that makes the determinant of this weird-looking matrix equal to 0. And this isn't just some random busy work. Solving this exact problem is how you find something called eigenvalues, which are, well, they're a huge deal in linear algebra. All right, let's pull the camera back for our final section and see the grand unification of all this. Because here's the secret. Matrices are not just boring grids of numbers for solving equations. They're actually machines. They're little engines that can transform space itself. So what do I mean by transformation? Well, a linear transformation is just a special kind of function that takes a vector as an input and spits out a new vector as an output. Imagine you have a matrix that represents rotate everything 90 degrees. You feed it a vector, and out comes that same vector, rotated. And the coolest part is that basically any of these nice geometric actions, rotations, reflections, stretches, you name it, can be perfectly captured by a matrix. Okay, that's cool. But how do you find the right matrix for, say, a specific rotation? This is where it gets really beautiful and simple. You don't have to check what happens to every vector in the universe. You only have to check 2. You just look at where your transformation does to the most fundamental vectors there are, the standard basis vectors. In 2D, that's just the vector 1, 0 that points along the x-axis, and 0, 1 that points up the y-axis. And here's the punchline. You take those 2 basis vectors, you see where the transformation sends them, and those results, they literally become the columns of your matrix. The new location of 1, 0 is your first column. The new location of 0, 1 is your second column. It's just so elegant, it feels like cheating. So let's just quickly recap the journey we've been on. We started with a basic system of equations. We learned how to solve it with Gaussian elimination. That process revealed the idea of rank, which told us how many solutions we have. Then we found a magic number, the determinant, to test for invertibility and unique solutions. And finally, we zoomed out to see that all this algebra is really just the language of geometry, of transformations. It all connects. And I'll leave you with one final question to think about. We know the determinant tells us about invertibility, but if a matrix is a transformation, say it stretches a square into a parallelogram, what do you think that number, the determinant, tells you about how the area has changed? That's where things get really interesting. All right, good luck on your exams. You're going to do great.